America made a decision. It decided that if China could not access the tools required to build advanced chips, China could not build advanced chips. The logic was straightforward. The equipment required to manufacture cutting-edge semiconductors is so specialized, so technically demanding, and so concentrated in the hands of a small number of Western companies that cutting off access to it would effectively freeze Chinese chip development at the level it had reached and let the gap between Chinese and Western capability widen until it became permanent. The policy that followed was comprehensive. Export restrictions on the most advanced chip manufacturing equipment, diplomatic pressure on allied countries to enforce the same restrictions, sanctions on Chinese companies that attempted to find workarounds, a coordinated effort involving the United States, the Netherlands, Japan, and others to ensure that the one machine capable of printing the most advanced chips on Earth would never reach Chinese soil. American officials described the policy as effective. American analysts described the gap it was designed to create as insurmountable. The semiconductor industry, watching what was unfolding, largely agreed. The tools China needed were out of reach. The chips China could build without those tools had a ceiling. The ceiling was low enough that it would keep China permanently behind in the technology domains where chip capability matters most. That was the consensus. Here is what happened next. Stay with me. Because the full story of what China did in response to being told it was impossible is more interesting, more technically sophisticated, and more consequential than anything the headlines have captured. And the part that nobody saw coming is not the part you think it is. Hit the like button right now before we go any further. This research takes serious time and directly helps this reach people who want to understand what is actually happening at the frontier of the most important technology competition of our era. Subscribe and turn on notifications. This story is only beginning to unfold, and you want to be there for every chapter. Let us get into it. To understand what China proved, you first need to understand what America was so confident was impossible, because the confidence was not arrogance. It was based on a genuine understanding of how chip technology works and why the tools that were restricted are so difficult to replace. For 60 years, the semiconductor industry ran on a single organizing principle: make transistors smaller and everything gets better. Smaller transistors mean more transistors fit on the same chip. More transistors mean more computing power. More computing power in the same space means lower cost per unit of computation. The cycle repeated with remarkable consistency for 6 decades, doubling chip capability every 2 years with a reliability that made it feel less like engineering progress and more like a law of nature. Gordon Moore described this pattern in 1965. It became known as Moore's Law, and it held, with variations and occasional stumbles, for longer than most people who understood its implications believed it could. The reason it held was that engineers kept finding ways to print smaller and smaller patterns onto silicon. The machine that makes this possible is a lithography system. It works by using light to project a pattern onto a light-sensitive coating on a silicon wafer, similar in principle to how a film camera exposes an image onto photographic film, but at a scale that requires the most precise engineering in human history. The challenge is that light can only print details as small as its own wavelength. To print smaller transistors, you need shorter wavelength light. To get shorter wavelength light, you need more energy. The progression of lithography technology over 60 years has been a progression toward shorter and shorter wavelengths, each generation requiring more sophisticated and more expensive equipment to produce and control. The current pinnacle of this progression is extreme ultraviolet lithography, EUV, made exclusively by a Dutch company called ASML. The machine produces light with a wavelength of 13.5 nanometers by firing a laser at droplets of molten tin at 50,000 droplets per second, creating a plasma that emits the required wavelength. That light is then directed through optical systems, machined to a precision measured in fractions of an atom, and used to print circuit patterns too small to see with a conventional microscope. Each machine costs approximately $200 million. ASML produces fewer than 60 per year. The entire global supply goes to TSMC in Taiwan, Samsung in South Korea, and Intel in the United States. These 3 companies use EUV to manufacture the most advanced chips on Earth, the ones in the latest iPhones, the ones powering the AI revolution, the ones that everything at the frontier of modern computing runs on. Huawei cannot buy an EUV machine. SMIC, the Chinese manufacturer that makes Huawei's chips, cannot buy one either. The export restrictions prevent it. The machine that makes the chips that matter most is permanently unavailable to the companies that most want it. This is what America was confident could not be overcome. Now watch what Huawei did instead of accepting that conclusion. The first thing Huawei and SMIC did was push the tools they were allowed to keep further than anyone believed possible. The older generation of lithography machines, called DUV for deep ultraviolet, use a longer wavelength of light and cannot print as small as EUV machines can. The semiconductor industry's conventional wisdom held that DUV had a practical ceiling, a point beyond which the physics of the longer wavelength light simply could not be pushed further. SMIC pushed past that ceiling. They used a technique called multi-patterning. Instead of printing a chip pattern in a single exposure, they break the pattern into multiple simpler sub-patterns, each one printed separately with perfect alignment and then combined. The analogy is painting a detailed mural not in one pass but in multiple layers, each layer adding detail that combines with the others to create the complete image. The alignment between layers has to be accurate to within a fraction of a nanometer or the whole thing fails. Through what can only be described as extraordinary engineering persistence, SMIC pushed DUV multi-patterning to produce chips roughly equivalent to a 7-nanometer process. Most independent experts had considered this beyond the practical capability of DUV before SMIC did it. The chips that resulted powered Huawei's Mate 60 Pro smartphone, a launch that surprised the global semiconductor industry when benchmarking revealed the chip inside was considerably more capable than the export restrictions were supposed to allow. But SMIC and Huawei knew this was not the long-term answer. Every additional multi-patterning step adds manufacturing cost, increases process complexity, and reduces the yield of working chips per wafer. There is a ceiling to how far this approach can go. And Huawei's engineers, rather than continuing to push against that ceiling, started asking a different question. A question that nobody in the mainstream semiconductor industry had seriously asked at this scale before. What if transistor size is not actually what determines chip performance? This sounds like it should be obviously wrong. The entire progression of semiconductor technology for 60 years was built on the assumption that smaller transistors equal better chips. If transistor size is not the key variable, what was everyone optimizing for all that time? Here is the thing. They were not wrong that smaller transistors produce better chips. Smaller transistors do produce better chips, but for a reason that is more nuanced than most explanations capture. Smaller transistors are better primarily because they are closer together, and being closer together means signals have shorter distances to travel between them. Now, here is the insight that Huawei built their new approach on. If the benefit of smaller transistors comes primarily from shorter signal distances, then there might be a way to get shorter signal distances without making the transistors smaller at all. What if you could take the same transistors, the same manufacturing process, the same chip that SMIC already knows how to make, and rearrange where those transistors sit relative to each other in a way that makes the distances between them dramatically shorter? Not by shrinking them, by stacking them. This is the idea. And once you see it, you cannot unsee it. Take a piece of paper covered in text. The word in the top left corner and the word in the bottom right corner are separated by the full diagonal length of the page. Now fold the paper in half. Those same two words are now separated by nothing but the thickness of the paper. The words did not move. The paper did not change. You just changed the spatial relationship between things that were already there. Huawei's engineers applied this logic to chip design. Take the logic components of a processor that would normally be spread across a single flat layer of silicon. Divide that logic into two halves. Stack one half physically on top of the other. Components that used to communicate across several millimeters of flat silicon now only have to communicate across the tiny vertical distance between the layers. Millimeters become microns. Signal distances shrink by a factor of 1,000. When signal distances shrink, signal travel time shrinks. When signal travel time shrinks, the chip performs more operations in the same time period. When the energy spent moving signals around shrinks, more of the chip's power budget can go toward actual computation. When the heat generated by signal movement shrinks, the chip runs cooler at the same performance level. Huawei calls this approach tau scaling. The name comes from the Chinese word for time, reflecting that the optimization is for the time signals spend traveling rather than for the physical size of the transistors doing the computing. Their early results show a transistor density of 238 million transistors per square millimeter using this approach. Approximately 55% more computing capability packed into the same physical footprint compared to their conventional flat chip design. On their roadmap extending to approximately 2031, they are claiming this approach could deliver performance equivalent to what the industry would describe as a 1.4 nanometer chip without EUV, without ASML. Without any of the equipment, the export restrictions were designed to deny them. Let that sit for a moment, because we are not done. Here's the number that made every semiconductor engineer who saw Huawei's presentation stop reading and look again at the slide. Not 1.4 nanometer. The other number, 1.5 microns, this is the bonding pitch Huawei is targeting for the connections between their stacked chip layers. And you need to understand specifically why this number matters before you can understand why the announcement is being taken seriously by people who were initially skeptical. When you stack two chip layers on top of each other, those layers have to communicate constantly. Every calculation requires signals to pass between the layers billions of times per second. The connections between layers are made through tiny copper contacts bonded directly from one surface to the other. The smaller those contacts can be made and the closer together they can be placed, the more connections you can establish and the faster and more efficiently information can flow. The spacing between those connection points is called the bonding pitch. The current best in the world is approximately 9 microns. That is what AMD uses in their three-dimensional V-Cache technology, which is currently the most impressive commercial implementation of chip stacking available. TSMC and Intel are working in the same range. Huawei is claiming 1.5 microns, 6 times smaller than the current world-leading benchmark. Achieving 1.5 micron bonding pitch requires new materials, new equipment, new bonding processes, and new methods for verifying that the connections form correctly at that scale. The progression from where the industry stands today to 1.5 microns represents the kind of advance that would normally take a decade of progressive incremental improvement. Huawei is presenting it as a near-term target. Here is why this is the number that matters. If Huawei achieves 1.5 micron bonding pitch at production scale with acceptable yield, two stacked chip layers stop behaving like two separate chips communicating with each other. They start behaving like a single, unified processor that happens to occupy two physical layers. The boundary between them disappears from a performance standpoint. The full vision of what tau scaling promises becomes achievable. If they cannot achieve it, the approach is limited in ways that prevent it from delivering the headline numbers. The 1.5 microns is where the proof is. Now the honest part. The part that the versions of this story that want it to be a simple triumph leave out. Before you conclude that China has definitively proven America wrong, you need to understand the specific problem that could prevent everything described above from becoming real. Physics, specifically heat physics. Here is something most people do not think about when they think about chips. Memory chips, the components that store data, run relatively cool. They switch infrequently, their power consumption is modest, and the heat they generate is manageable. Logic chips are completely different. A logic chip running at full speed is switching hundreds of billions of transistors every second. Every switch generates a tiny pulse of heat. Multiply tiny by hundreds of billions per second, and you have a component that generates enough heat to destroy itself if not continuously cooled. In a data center server, this is a solved problem. There are liquid cooling loops, massive airflow systems, entire building designs organized around moving heat away from processors. The thermal management challenge is significant, but the infrastructure to address it exists at scale. In a smartphone, none of that exists. Your phone has a thin metal frame, a graphite heat spreader, and the air around it. The entire thermal budget of a smartphone chip is constrained by what the user's hand can tolerate in terms of surface temperature. The chip has to stay cool enough that holding the phone does not hurt. Everything the chip does has to fit within that thermal envelope. Now stack one logic chip directly on top of another logic chip. The heat from the bottom layer has nowhere to go. The top layer is sitting directly on it, generating its own heat and blocking the path that the bottom layer's heat would normally take to escape. You have created a thermal problem that is fundamentally more difficult than either layer would present individually. This is the challenge that no major semiconductor manufacturer has solved for commercial logic-on-logic stacking at the density Huawei is targeting in a mobile application. Some research teams have demonstrated approaches in laboratory conditions. None have proven them at the production scale and yield required to manufacture smartphone chips commercially. Whether Huawei has a credible thermal management solution for stacked logic chips in a mobile application is the question that the entire credibility of the 2031 roadmap depends on. Their announcement addressed the concept. It did not provide the detailed thermal management solution that would allow independent engineers to assess whether the mobile implementation is genuinely feasible. That is not a reason to dismiss the announcement. It is a reason to hold the full conclusion until more information becomes available. The history of semiconductor engineering is full of problems that looked insurmountable until someone solved them. The thermal challenge in logic-on-logic stacking may be one of those problems. Or it may be a genuine ceiling that constrains the approach to applications where more robust cooling is available. The honest answer is that we do not yet know. And anyone who tells you they do know is telling you more than the evidence supports. Here is something important that almost no coverage of this announcement has mentioned. Huawei is not inventing a new direction for the industry. They are accelerating a direction the industry was already moving in. AMD stacks memory on logic in their processors today. The three-dimensional V-cache technology adds a cache memory layer on top of the processor die, and the performance gains in the right applications are substantial enough to have made it commercially successful. Intel has a program called Foveros that stacks chip components vertically. TSMC has a program called SoIC doing the same. High bandwidth memory used in the AI chips that are currently the most commercially valuable semiconductors on Earth stacks up to 12 memory layers on top of each other. The industry was already building in the direction Huawei is now pushing. What distinguishes Huawei's approach is three things. First, they are attempting to stack logic on logic rather than memory on logic. This is significantly harder because of the thermal problem described above and because logic chips are more sensitive to the signal integrity challenges that bonding introduces at high density. Second, they are claiming a bonding pitch of 1.5 microns, 6 times smaller than the current commercial benchmark. If they achieve this, it is a genuine world first that would change the competitive picture in chip packaging technology. Third, they are doing this under export restrictions that prevent them from accessing the equipment that would otherwise be their path to more capable chips. The necessity of this approach, not just the ingenuity of it, is what makes it genuinely unprecedented. The industry was going this direction anyway. Huawei is attempting to leap ahead of where the progressive improvement path would have taken everyone else by 2031. Whether they land the jump determines whether they proved America wrong or demonstrated that the wall America built was higher than it appeared. The geopolitical dimension of this story sits underneath all of the technical details and deserves to be stated directly. The export restrictions on Huawei were designed around a specific theory about how technological advantage works. The theory was that capability in chip manufacturing creates compounding advantages that, once lost, cannot be recovered without regaining access to the manufacturing tools. Control the tools, control the chips, control the chips, control the applications, control the applications, control the data, control the data, control the future. The policy that flowed from this theory was designed to ensure that China could not regain access to those tools and therefore could not close the capability gap that the restrictions were intended to create and maintain. Tau scaling, if it works, challenges not just the specific outcome the policy was designed to achieve, but the underlying theory it was based on. If there is a path to competitive chip performance that does not run through EUV lithography, the premise that controlling EUV lithography is sufficient to control the competitive trajectory of Chinese semiconductor development is wrong. This does not mean the restrictions were a mistake from America's perspective. The restrictions have slowed Chinese chip development and created genuine costs for Chinese technology companies. The gap that the restrictions were designed to maintain exists and is real today. What Huawei's announcement suggests is that the gap may not be permanent in the way the policy assumed. That the room the restrictions locked China out of may have a door that the policy did not account for because it was looking at a different room. Whether that door leads where Huawei believes it does is a question that the next 5 years will answer. The roadmap runs to 2031. The thermal management question will have an answer before then. The yield question on 1.5 micron bonding will have an answer before then. The actual performance of a stacked Kirin processor, if one ships, will have an answer before then. What we know today is that the announcement is real, the engineering is serious, the numbers, while requiring important context to interpret correctly, are not fabricated. And the direction of the approach is one that engineers at the most advanced chip companies in the world are taking seriously enough to accelerate their own programs in response. Now pull back and look at the complete picture. America said it was impossible. They said it with confidence grounded in a genuine understanding of how chip technology works and why the tools they restricted are so difficult to replace. The confidence was not unreasonable given what was known at the time. What China did in response was not find a way around the specific obstacle America placed in front of them. It was find a different path that bypasses the obstacle entirely by going somewhere the obstacle was not designed to block. That is a different kind of response than the policy anticipated. And it is the kind of response that is genuinely difficult to design against in advance because it requires imagining approaches that have not been tried before. The honest summary is this. Huawei's Tau scaling announcement is real engineering aimed at a real problem with a genuinely novel approach. The early density numbers are real. The 1.5 micron bonding pitch target is the genuine frontier of what the announcement claims and the genuine test of whether the claim is achievable. The thermal challenge is a genuine obstacle that the announcement has not fully addressed. The roadmap that extends to 2031 is ambitious. Whether it arrives on schedule, arrives late, arrives partially, or does not arrive as described will depend on engineering challenges that have not yet been solved. What has already been proven is the part that should make every semiconductor engineer and every policymaker sit with this announcement carefully. The assumption that being cut off from one specific path to chip advancement meant being cut off from chip advancement itself turned out to be wrong. Not because China found a way through the wall, because China found a room the wall was not built around. Whether that room has everything they need is the question the next few years will answer. But the room exists, and that by itself is the part America said was impossible. If this gave you a genuinely new way of thinking about what is happening at the frontier of the most consequential technology competition of our time, hit the like button. It matters more than you might think for getting this content to the people who want it. Subscribe and turn on the notification bell because the next chapter of this story will break without warning and you want to be there when it does. Drop a comment and tell me honestly, do you think Huawei actually solves the thermal problem in time for the 2031 roadmap? I read every single one. See you in the next one.